In manufacturing plants around the world, chemicals are brought together, their molecules coaxed to react to create new molecules that will ultimately give rise to our foods, our medicines, our shampoos, our clothes, and our phones. The methods that we use to combine those chemicals have a lot to say about how sustainable any of those products can ultimately be. In this episode of Green Chem Essential, a look at mechanochemistry, a suite of chemical processing methods that are rooted in our ancient past, but which are being investigated anew for their potential to make those manufacturing systems cleaner, safer, and more efficient. I'm James Ray, and I'm joined by Wilfried Braje, a research fellow with AbbVie, and Isaiah Speight, an assistant professor of chemistry at William & Mary. Isaiah, Wilfried, welcome and thank you very much for joining us.
Thank you. Glad to be here.
Super excited to talk with you.
Wonderful. Well, Isaiah, I'm going to turn it right to you. Mechanochemistry. Tell us about mechanochemistry, please.
I think mechanochemistry is probably an older technique than people know of or think of. If you do a quick Google search for just chemistry itself, you tend to see images of bubbling flasks and, colorful solutions and all of this fancy exotic glassware. But before we got to a point where we were doing chemistry in these, very niche ways with different solutions and stirring things and mixing things, man had to start from somewhere. Scientists had to start from somewhere, and that started from mashing things together. And that's really the origins of what mechanochemistry is doing reactions and creating new products using mechanical force. We grind things together, we mash things together, and that's how we do reactions. And the real fundamental precipice of it is that we can do these reactions in in some cases a safer way, a more environmentally friendly way, and in a way that makes chemistry more sustainable overall.
Thank you. And we're going to certainly dive much, much deeper into that, all of this, but especially that last piece is why this becomes such an important topic when we're talking about the sustainability, the climate change impacts of manufacturing processes, again, to get the things that we need in our lives. There's something, Isaiah, that you mentioned there that, again, when we talked before this interview, that I love is how old mechanochemistry goes to the roots of humankind. And you mentioned even scientists. We can take it way back to before we would consider anyone a quote unquote scientist. I think you mashing berries on a stone, right?
Right.
Or mashing plants or whatever it might be on a stone or whatever to get the earliest pigments or dyes that people have used in ancient times. Am I right?
Yeah, exactly. I mean, when you think all the way back to, early herbalists and how they would grind up plants to make medicines for people, or early artists, how they would take different resources from nature and grind them up to make new colors and pigments. We weren't thinking about it then as doing chemical transformations, but in some cases you are. And there are reports extremely early on of people actually doing chemical transformations. Um, but we didn't think about it as tried and true science and chemistry until maybe about 15, 20 years ago, when we were able to use this technique in a more methodical way with upscale lab equipment and techniques. But this thing has been around, this concept has been around forever. I mean, even when you think about chefs in kitchens, you grind up spices and you make spices to season foods and prepare things. I tell students all the time, you think about solutions because they're constantly in everything you do. When you bake cakes, you typically add water and oil and eggs, and when you make your cereal, you've got a solvent of milk that your cereal sits in. But there's so many other ways that we do chemistry in the solid state. When you make freshly ground pepper, you're doing a mechanical action to get to that finer particle. And so the same holds true for how we do mechanochemistry. We're just using it to make new molecules.
Wonderful. Isaiah, one more piece to that, and then Wilfried, I'll turn to you. Isaiah, so just to sort of firmly seat this opening introduction of mechanochemistry, um, there the different types of forces. I'm looking at my list over here that you told me earlier.
Yeah.
There's in the definition, it's the different types of forces that can be applied in mechano. It's shear. Do you know what I'm talking about? If you could
Yeah,
just
I do.
walk us through that list so we can get those in mind, and we'll come back to them later as well.
Yeah, so, when you talk to different types of scientists and chemists, they look at these forces differently, but they all do some similar method. All of this is classified as reactions that are promoted by mechanical force. And to your point, there are different types of forces. There are stretching forces, and that's really good for like the polymer community. There are shearing forces where you can slide two surfaces across each other and get reactions to happen between those. Compressive forces where we're pressing things together, and all of those different types of forces can promote different reactions and behave in different ways, which allows for such a diversity of doing reactions. Versus in solution, you have really one major motion, which is stirring, but you don't get any, directional component. You aren't getting an applied force that you can control. You just get stir. But in mechanochemistry, we have all of this different directionality that we can control, which allows our reactions to be really creative.
Yeah, and there's one that you didn't mention that you told me about before, and I want to mention just because again it anchors it in just the fundamentals of this stuff. I think kneading,
Oh, that's true.
the kneading force, and I'm not sure I'm mimicking kneading here right with my hands,
I think you are.
but again, it just that anchors it, in the fundamental human activity of baking bread, for as an
Right.
example. All right, so if mechanochemistry has its roots in our ancient past, and is so clearly powerful and useful in our lives, the question then becomes, why is it? Why are we talking about it now in sort of like, hey, here's something new. Here's a new idea for how we can manufacturing things at a large scale to bring us our products and the things we use in a more sustainable way. Wilfried, I'll turn that to you if I and you can take it to maybe in the manufacturing setting, what we have to be doing. Why is how did we get away from mechanochemistry? Why has it not been used in traditional processes over the past 100 years, let's say? Take that as you would, please.
I think traditionally, or in the industrial revolution, basically we had, as chemists, we had to solve the solubility challenge, because only reactions or the dogma is until now probably is anything that is dissolved in a solvent can react in a chemical reaction. Because I think if you swallow a brick stone, or if you put a brick stone in a vessel and you want to make a chemical reaction, that's pretty hard because the brick stone is a brick stone and it has not dissolved. So that is the key to get a chemical reaction to work, is basically thought of as we need to dissolve it. And that's where organic solvents, which are derived from the petrochemical industry, that's where they're very efficient at. And that's where the history comes from, that we traditionally do all the manufacturing of drug when we produce them, is that we rely on organic solvents because they help us to solve the solubility challenge and enables us to do chemical reactions that ultimately gives us drugs.
Wonderful. And Wilfried, I'd like to keep it with you for a second. And I love how you anchor us back to the Industrial Revolution, and later, I suppose, or the advent of petrochemicals, and this idea that to combine things, they needed to be thrown in a solution and dissolved, I guess, right? So, and that was the way to combine things. Because, and I sort of hinted at this in our opener, but what do you, whether it's in your field of pharmaceuticals or any other manufacturing field, what's trying to happen in those large vessels where you're dissolving things in these solvents? What the goal is to do what?
Yeah, the goal is to take a starting material, let's call it A, and another reagent that we need B to get a product C. That is, and C ultimately is the drug. It's as simple as that.
Simple as that, but Wilfried, why not so simple though? Because I mean, there are this is another topic, but for example, water as a solvent,
Right.
even if you're talking about dissolving things, combining A plus B to get C isn't, sometimes they just don't want to combine, right? You need specific ways to do that. So Wilfried, that's been the role of what, the petrochemical based solvents, is that right?
Exactly. That's originally where they're very good at. And I think now we are learning also inspired by nature because chemistry in our bodies is happening in water, as you were saying. That's another area of green chemistry where the field has recognized that we can use many advantages of chemistry in water because it's a benign solvent, which is not always the case for these organic solvents because they are derived from the petrochemicals. So that oftentimes they're toxic and you have to buy them, you have to dispose them. So that's why we try to get away from using organic solvents.
All right. So, and Wilfried, you just hinted at it actually in terms of, okay, so why are we now trying to get away from solvents? You started to go down that path. Isaiah, do you want to pick up on that at all in terms of if the impetus now is to return to, again, an age-old method of mechanochemistry and bring it into modern times and modern uses, in a much larger way than even has been done in recent years? What is from a sustainability perspective, what's driving the interest in this? Wilfried, if you want to keep going, or Isaiah, whoever wants to pick up on that.
Yeah. So yeah, what did you go
Yeah,
ahead?
I'll gladly jump in. So I guess the biggest driving force is safety of the manufacturer, safety of the scientists who are making your day-to-day products, and also safety of the end user, right? And when I say the end user, not just the person who buys the product and picks it up off the shelf, but the people who are living in the communities around these, plants and around these manufacturers. When you look at how waste gets disposed of after reactions in a typical, lab setting, in a teaching lab or in an academic research lab, you have smaller amounts that you can bottle up and your health and safety organizers will come and pick them up and dispose of them. But when you're doing reactions on kilogram scale, you have reactors almost the size of your living room. That waste pickup and that waste production becomes a problem. And what we're seeking to do by getting back to mechanochemistry, or as Wilfried alluded to, all of these other methods of green chemistry, such as chemistry and water, we want to make whatever that waste footprint is either smaller or easier to handle. And so with mechanochemistry, as Wilfried mentioned, you have a reduction in what solvents you're using. You don't have to use multiple liters and liters and tanks of solvent, but you can literally use none, or in some cases, a very small amount to make reactions go. And with that reduction in solvent waste, now you've dramatically shrunken the footprint of doing chemical reactions.
Thank you very much. Wilfried, is there anything you wanted to add to that before I move on to my next question?
Yeah, I think important is to understand the role of the solvents, and about 60 to 80% of the waste that's being created in a chemical reaction is related to the use of solvents. And that's why I think it's so important that we try to minimize the use of solvent because that equates to waste, and that, of course, is not desirable.
Not desirable from Isaiah. I love you took us towards environmental justice on us, as you mentioned, sort of
Yeah.
fence line communities. You took us to the users of products, the workers on a production line, and I'll throw out there. I think you all have hinted at least is certainly, and it's a reason why industry has been in that it's that waste equals dollars, and dollars.
Yeah.
It's everyone's interested in making their manufacturing processes more efficient. Wilfried, is that a fair statement?
Yeah, and I think that is a great driver because it's creating a win-win-win situation for everybody, for the society, for everybody, also for the industry. And that's why I'm thinking this is a process that will prevail and will advance because in the end, the incentive for companies is that it lowers costs. And that I think is a great driver to implement green chemistry principles.
Terrific. All right, so let's bring the focus back to mechanochemistry. So we have it established, and I keep laughing, but I think there's a wonder to it in my eyes. There's sort of an elegance to it and a beauty to returning to something that is so firmly grounded in our ancient history, and trying to bring it, trying to adapt it or make it I'm, Isaiah, I'm struggling with the words here. Adapt it to modern times, make it useful at
Yeah.
large scale modern settings. How would you help me out here?
Yeah, I think that, like you said, it's a old tool, but it's got so much utility. And so I think when we look at chemistry, every chemist has a toolbox that they use. They reach in there and they grab different things from day to day. Your chemists that make, TVs and make screens, they use a different toolkit. When you look at people who make pharmaceuticals, they use a different toolkit. When you look at your chemists who make plastics and adhesives, they use a different toolkit. But the root toolkit that everyone uses is chemical synthesis. As Wilfried said, taking A, mixing it with B, creating C. And in all of those processes, there is some level of waste, there is some level of, byproduct that's formed that you don't want. And everybody, no matter what your background is working to reduce that piece, to make chemistry more efficient, to make chemistry more safe. If you look back in the beginning days of chemical synthesis, people were using some really nasty reagents. And over time, things have gotten a lot more sustainable from what we're using. But now the challenge as chemists is to make the actual reactions we're doing safer and sustainable, but also think about where we're getting our resources from to do chemistry. And all of that ties into mechanochemistry. As Wilfried said, the solubility piece has always been the biggest problem. Chemists have been searching forever for a universal solvent that they could do every reaction in and never have to think about it. And we haven't gotten there yet. But to think about it in a contrarian way, maybe the universal solvent is no solvent. And that's where mechanochemistry really starts to fit itself in, where we can start looking at reactions we can do that typically were either hindered by a solvent or maybe don't like a certain solvent, or our reagents may not behave well in certain solvents. And by removing that barrier, now we've opened up even more doors for doing chemistry. We just have to take more time to explore that landscape because it's such a vast space. We don't know where we can go next. And so we're really just in the exploratory phases right now.
I love that that concept. The new solvent is no solvent, perhaps.
Yeah.
And so I guess the idea is again, you're taking if A plus B equals C. Typically, you'd bathe A and B in a solvent to get C, but now you're saying never mind the bath. Let's just put them on a plate or on a surface and knead them, push them, take me.
Mash them together.
Yeah. So
Exactly.
maybe in your lab, then, what if there's a way to do this so that folks who don't have a technical background can stay with us here, stay,
Yeah.
and myself included, by the way. Um, are there some examples in your lab that where you're doing this, and sort of what kind of forces you're bringing to bear to get any sort of an output that we might be somewhat familiar with?
Yeah, there are a couple of different pieces of equipment that we use, tools that we use, but the one that's the most common that you'll find in almost any chemical lab, and as Wilfried said before, in a lot of kitchens, is a mortar and pestle, right? When people grind up spices at home, you take peppercorns and you drop them in your bowl and you grind them up and mash them up and make smaller pieces of pepper. That's some of the same equipment that we use in our labs. Now, the materials and the surfaces may be different, but the same mechanisms of action still apply. And there are a lot of chemical reactions that only require just general elbow grease and arm work. There are some reactions that require a little bit more of a push, and that's where we scale into mechanical equipment. And we use equipment that are called ball mills, where you take your reagents and you put them in jars that are no bigger than, maybe a typical capsule holder for when you pick up your medicines from whatever your pharmacy is. That's about the size that we're working in, and you load your chemicals inside with some form of milling media, typically a sphere that's made out of stainless steel or minerals or things of that nature, and we just shake them really hard. That's really where a lot of our chemistry starts. As you start to get on larger scale, the equipment becomes more complex, but we really just get in the lab and shake things. And so I tell students that come and want to work with me, our lab is no different than a rage room. We just have much more confined parameters for how we do things, but we just shake the chemicals really hard and see what comes out.
Wonderful. And Isaiah, I want to come back to the see what comes out part because there's something you'd mentioned when I talked to you previously that's really wonderful there. But Wilfried, I want to take it back to you if I could, please, because Isaiah hinted at the I think what really becomes the challenge. I'm assuming I think
Yeah.
is that the scale up part. So if Wilfried's in a lab at William and Mary, as he said, shaking, pushing, sliding, whatever it might be. But Wilfried, you're in the pharmaceutical industry where things have to happen, and so I'd like to ask you. I guess there's two parts to this question. I'm honestly not sure which way you're going to take me on it, which is, are there examples in which you're successfully using some of this now in a commercial setting, or what are some of the barriers to that answer being yes? Whichever way you'd like to take it, because I want
Yes.
this idea of taking this technology into a manufacturing process, scaling it up so that it meets the needs of a pharmaceutical manufacturer or any other type of industry out there.
Yeah, one of the limitations is that we still are finding out the rules for mechanochemistry, I would say. Also, because it needs to be, especially when you design or when you produce drugs, it needs to be very reliable. And I think that's something we are exploring now. We see the benefits of mechanochemistry. And as you said, one of the initial early concerns was that you can do it in a batch environment, but that it'll be really difficult to scale it up. But recently, also when we look at other industries, we learned that using reactive extrusion, and I'm sure that Isaiah can talk a little more about reactive extrusion and how important it is, because it takes the reaction into the flow. And that means that you can produce much larger volumes using the same principles. But maybe Isaiah can speak a little more from the transition from ball milling towards reactive extrusion, from batch processes to flow processes.
Before we do that, Wilfried, earlier when we talked, you mentioned, you hinted that there actually are, at least in your industry of the pharmaceutical industry, there are folks who are experienced in mechanochemistry. Could
Right.
you, again, for folks who aren't familiar with the inner workings of a pharmaceutical manufacturing process, where has it already been in use?
Yeah, it's been around for about 30 years in the departments of formulation sciences. That means once you have the drug molecule or the active pharmaceutical ingredient, and then you need to put it into a tablet. And that process that's where mechanochemistry, and that's actually also where reactive extrusion, where you have the flow process. So a tablet is being pressed, and then at the end of the process, it drops out. That's where we have experience using reactive extrusion. And that's actually the machines now that we use for producing the drugs also.
Okay. So I want to come back to help myself and others understand reactive extrusion. But Wilfried, you mentioned so the folks who are already have been using mechanochemistry, and I guess again you hinted earlier at this. You're able to now, in addition to Isaiah and the folks in his lab and other places, and their expertise, you have some expertise in house of folks who can lend their idea to, hey, here's how we can expand use of it in our processes. Is that fair to say?
Yeah, but of course there are limitations. There are experts in formulating the drugs to prepare the tablets, but now the new challenge is how can we apply these principles to the synthesis of drugs? And that's where the learning is ongoing right now. I think we all see the potential. That's also where I like the efforts within the industry. So basically, there is the Pharma Roundtable from the American Chemical Society. So that's where we get together and also discuss these new technologies where we see a lot of promise. And that's actually where we team up so that not every company has to reinvent the wheel, but that's the beauty is also that's where we work with academic groups. And I think that to me is so important that we work as a community to bring these new promising technologies to full blossom, so to speak.
Wonderful. And for folks watching or listening to this, there is another episode that focuses specifically, or that also references, I should say, the pharmaceutical roundtable. And it's this group of people who are competing, you know, very full force competition in the marketplace, but who nevertheless have been able to come together to work on kind of the behind the scenes manufacturing of those things in a very powerful way. Wilfried, thank you for bringing that up. Wilfried, before we move back to Isaiah, I want to make sure myself and folks watching and listening are understanding this. In terms of where mechanochemistry is already being used and where the challenge lies, I think if I heard you right, it's the mechanochemists, as you said, for 30 something years have been taking, once you have a drug synthesized, they're now grinding whatever the force might be to put it ultimately into its pill or its capsule, that sort of thing. Is that fair enough?
That exactly is the process.
Okay.
That's very well established.
But now the sites have turned to actually making the compounds that get to those folks with mechanochemistry, which has traditionally been done in the solvents and with all its accompanying challenges.
Right, exactly. And
Okay.
that's where all the unknown is right now. So
Yeah.
how does it really work? What is important? So that's
Yeah.
what we are learning right now.
Wonderful. All right. Well, that brings us perfectly, Isaiah, back to you, because when we talked previously, you said when you engage, when you take A and B and you gauge in mechanochemistry, there are a few outcomes, things that can happen. One of which you identified as a particular. I don't want to. Do you know what I'm asking you?
I know exactly what you're talking about. So yeah, so when
Okay.
it comes to doing mechanochemistry, there are typically three main outcomes, three buckets that we can fall into. There's the bucket where your solution chemistry and your mechanochemistry behave the same. And that's where we typically like to be. Things are predictable, reactions that we know work continue to work. All we've done is remove the solvent, maybe changed a few small parameters, but the chemistry still behaves as we expected. There's the bucket that we can sometimes fall into where removing the solvent totally shuts a reaction down. And so that's where mechanochemistry and solution chemistry will radically differ. A solution reaction will work, a mechanochemical reaction will not. And that is where we're trying to understand what those major differences are. But the third piece is the one that I think is a little bit more unique, where a solution reaction with the exact same parameters can give you product C. In a mechanochemical reaction, you put together A and B, and the reaction not exactly doesn't work, but it does work to give you a new product in D. And now we need to understand what drove these reactions into two different pathways, so to speak, right? It's almost as if saying that you took all of the ingredients together to make a cake, you put it in the oven, and instead of getting a cake out, now you've got a pie. What happened here? There's still delectable items that I would much rather have, but where did we change? What made a major difference here? And that's what we're really exploring in mechanochemistry and in the fundamentals of mechanochemistry.
Okay. So the idea again, you're still different outcomes, both potentially of use,
Yeah,
but a bit of a surprise there, and trying to figure out why you're getting that surprise.
And I
right.
think that is a very
And
important point that Isaiah just mentioned is that we see added benefits when using mechanochemistry. For example, if a reaction is much cleaner, because also where a lot of resources and waste is being created is when you have to clean up a product. And that's if you can avoid that, if the reaction is so clean that you have minimal cleaning to do, that is a huge benefit. And that's actually also where we try to see where is mechanochemistry giving us this additional benefit, also where it has clear advantages over all the other technologies, also the green technologies that we are trying out.
Certainly. Does Isaiah, there was a playfulness to the pie outcome, I guess we'll call it, the
yeah,
mystery outcome, the mystery outcome, the surprise outcome. It sounded when I talked to you before that that was kind of your favorite space to play in right now.
it
Um,
definitely is.
am I correct about that, and why?
You're definitely correct. And it's because it challenges what we already know. Taking a reaction that has worked the same way for, let's say, 100 years, and saying, let's try this thing without solvent, and you get a new product is wildly fascinating. It challenges what we know. It forces us to get uncomfortable as researchers and to really explore how reactions work and happen. There's so many different things that we do on a day-to-day basis that should go a certain way, And there's that one time that it doesn't, and you've done everything the exact same way, but you get a different outcome, right? What happened there? And it causes you to sit and be puzzled, and you turn your head to the side a little and you look at this thing and you say, why is this different now? All I changed was one little thing. And that's how we as chemists start to find new areas to explore. But the beauty of this is, now that we've got this new reactivity, we can now essentially pull a lever and say, I want to go in this direction, I want to go in that direction, almost like when operating train tracks at a major junction, right? I've got the same train, but if I want to go northbound, I'll push the lever up. If I want to go southbound, I'll pull the lever down. All I've changed is one thing, but now I've got multiple avenues to access. And that's where the most exciting piece to me in this mechanochemistry space is now I can take reactions that have worked a certain way forever and push them in new directions.
That's
Or
interesting. Yeah,
ensuring
Wilfried,
that the
please.
trains are actually on time. That's speaking, so to speak, to robustness, because we also need to ensure, if we have processes, no matter which technology we use, because when we produce drugs, we always want to ensure the highest quality, of course, because we want to minimize the amount of time that we spend and resources want to clean up things. So that's why it's so important also. And that's another layer that we're exploring, is giving mechanochemistry us a better robustness.
And when we say robustness, Wilfried, what do you mean by that?
I mean, oxygen, for example, some reactions are very sensitive to oxygen or to moisture or any other kind of contamination that may happen, especially when you work on large scale. To ensure an environment where there is almost no oxygen around is quite time consuming and costly in the end, also, because you have to bubble through nitrogen through the solution to ensure that there is no oxygen in the solution. If you can simplify that, when you have no solvent around, and then it's a lot easier to ensure an environment where there is no oxygen. That is a huge benefit.
So simpler, dare I say, more elegant manufacturing processes potentially.
Yeah, we
And
want
to
to
add to
buy.
that, speed, just generic speed, right? There are some examples of mechanochemistry where you have a reaction in solution that can take hours, where in mechanochemistry it can take minutes.
Yeah.
There's a uniqueness to mechanochemistry that allows reactions, as Wilfried has said, to be robust, and that robustness comes in a lot of different manners. But to me, and to a lot of folks in the industrial space, time is money, and we need things to react fast. We need things to react well. We need to generate chemistry that works at a high level. And all of that merges together into this image of what we believe mechanochemistry can be: a faster, safer, lower cost opportunity that also reduces waste. And I know we're kind of talking about this as this wonder mechanism of chemistry that'll solve all of our problems and eradicate all of the issues. But there's still a necessity to doing solution chemistry, because mechanochemistry can't solve all problems. But we're trying to better understand where that boundary exists, so we know when to implement mechanochemistry and when to stick with solution chemistry.
Yeah, another layer is also temperature. Many of the reactions we do in solution, we have to heat. And what we notice is that many of the reactions we do with mechanochemistry, we can do at room temperature, because it has this special forces that are involved. But as I was saying, we are at the very beginning of this journey to really understand all the rules of mechanochemistry. So there are many, many advantages, as we discussed, but it's also going to be a longer way actually to tame all these complexities.
That piece, I think, again, for the listeners, I think you're going to hear again and again in my episodes, because I've an episode that is yet to be recorded about battery research, and
Mm,
it's what Wilfried just said, which is the things that we have yet to learn, even though mechanochemistry has been around for thousands and thousands of years. And again, in the battery world, the researcher that hopefully you'll see in an episode speaks about people have been making batteries for a long time, making really better and better batteries, but there are still fundamental things that are left the unknown underneath the surface and the surface and the surface, that
yeah.
if we can discover those, make it all potentially better. So I love, that's really fascinating, Wilfried, that even in this age old thing, there's this we know mechanochemistry, but we also know that there are things about it we don't know yet that can maybe unlock some locks. I'm not sure. We should head towards wrapping up, but I want to close with a question of both of you. And Wilfried, maybe I'll start with you if it's okay. As you look to the future and the potential of mechanochemistry in particular, in your industry, or you can broaden it out to industry, processing, manufacturing in general. Um, is there anything in particular you're excited about or you're hopeful for? Is there a tipping point coming? Take that question in any way you'd like.
I think tipping point is the right word, actually, because I think what has been recognized is by academics as well as in industry that there's a huge potential, and that the easiest way how we can make progress is when we work together. And I think that's why I'm really glad that there are different consortia, and I'm involved in some of them. And mechanochemistry nowadays is always included. And I think that shows that the promise is there. Another layer I would like to add is also as a cultural change, because I think it's really important that students early on in their education, when they study chemistry, are exposed to these new technologies. Because I think the barrier, if you want to try something later in your life, when you are the full-blown scientist, so to speak, is much easier if you have been exposed to that technology early on, and if you feel confident and familiar with that technology. That's where I'm very glad that Isaiah is working on that end with students that are highly motivated to change the world, so to speak.
Wonderful. Thank you very much, Wilfried. Isaiah, same question to you. As you look toward the future, short or long term, you pick the scale. Things you're excited about, things you're hopeful for, a tipping point you see coming, again, however you wish to take the question.
Yeah, I think, Wilfried has brought up a lot of excellent points, and I think the one that resonates the most is that culture shift, that paradigm shift in chemistry. Being able to expose younger scientists to these new tools, these new techniques, to get them to challenge what reactions are, going and reinventing what we teach in early organic chemistry classes. Every student that takes organic chemistry is taught to think about what solvent to pick for what reaction. But if we can teach them that there's an alternative method that doesn't require it, it opens up new possibilities. And what I've seen, even in my very early time as a research faculty, your students and those new fresh eyes on chemistry will come up with ideas that are wildly more creative than your own. I give my students projects and they run with it and they come back to me with new things almost every day. And so giving them these new tools at an earlier standpoint will allow us to change chemistry literally forever. In addition to that, I think the other side of the cultural shift or the paradigm shift is for the end user, and teaching them, to get away from the idea of chemicals bad. I don't want chemicals in my home. I don't want chemicals in my space, and teach them to think a little bit more selectively of, I don't want certain types of chemicals, or I don't want certain processes to make the things that I use, and thinking about how all of these pieces come together. You mentioned earlier on, not everybody thinks about so far upstream of how things are being made or how things are being obtained. And I think with these new technologies, mechanochemistry, chemistry in water, biocatalysis, electrochemistry, we're showing people that there's a lot more to how to do chemistry and how to do science that's going to make a really big change.
Yes, thank you. Big change indeed, because again, the what I love about this, the work you all are doing, and so many other topics within the field of green chemistry is, if these changes can be successful, if the potential for them to ripple through massive industries, and therefore by definition creating massive change toward the better, sustainability, climate change, etc. The potential is tremendous. A long way to go in many cases, less to go in other cases, but still tremendous. Well, listen, Wilfried and Isaiah, thank you very much for joining me today, and this fascinating look at making what's old new again, in tackling some really fascinating challenges, all for such a really wonderfully important purpose. Thank you very much.
Thank you. Had a good time.